but first and foremost, we have Catherine Cannizzo speaking about homological mirror symmetry for Theta methodologies.
Thank you so much for the opportunity to speak at this great conference. So I'm going to be talking about joint work with my collaborators, Hania Azam, Heather Lee, and Juchu Melissa Liu. So the origins, I'm going to start out by talking about the origins of mirror symmetry. Where did it come from in string theory? So physics has evolved over time to describe more and more types of physical behavior. There was classical mechanics, and then Einstein's theory of relativity to describe very large objects, or special relativity for very fast objects, quantum mechanics to describe light particles. So how do we have a theory that unites all of these? So there was a conjecture that string theory might do this. The idea is that much, much smaller than quarks on a scale of, say, from the universe atom going that much smaller, there are these very tiny strings that are vibrating. And we can't see them because they're so small. And they're actually moving in 10 dimensions. So we have 4 space-time, so 3-dimensional world plus 1 for time. And the idea is there's these 6 extra dimensions for the theory to work that are in a compact Calabi-Yau manifold. So Calabi-Yau just means that a certain curvature quantity, the first term class is equal to 0. So this hasn't been verified from a physical standpoint, but there's a lot of very interesting math that came out of this. And physics is now expanded to looking at quantum field theories more generally. So how do we measure the physics of a string? So the idea is we have something called a sigma model, which is a map from a Riemann surface. Here I've drawn a cylinder onto the target Calabi-Yau manifold X. And so the idea is we have this string. So as you move along the cylinder, the image under the sigma model is where that string is at time t. So we have this rainbow Calabi-Yau manifold on the right here. It's a 2-dimensional slice of something 6-dimensional. The way that the physics is measured is taking all of these sigma. So the space of all of these mapped sigma is itself a space that is integrated over, and you weight by the energy. So that's a derivative of sigma. And interestingly, there's a phenomenon called T-duality that says there's actually a pair of manifolds X and Y, which give the same partition function. So this is the foundation for mirror symmetry as studied in math. We have a pair of manifolds, and mathematically they relate to each other. So the mathematical formulation is, one of them is a complex manifold. So that means that in local coordinates, we have a way of multiplying by square root of -1. And it corresponds to the symplectic geometry on the mirror manifold. So symplectic geometry is more restrictive than differential geometry. Smooth functions can do anything. Symplectic maps are a little bit more restrictive. They have to preserve this, They have to preserve this symplectic form here. But the tangent space on a symplectic manifold is complex. So kind of to first order, there's a complex structure on a symplectic manifold. So here's an example of mirror symmetry. We're just talking right now about the complex structure on one and the symplectic structure on the other. So we start out with a 2 torus. So it's side lengths R1 and R2. The area is related to the symplectic form, so that's R1 times R2. And the complex structure, that's what happens when we rotate by 90 degrees, so multiply by I. We have a scaling by R2 over R1. So here's R2, here's R1. What T-duality is mathematically is you have a base, so the base is R2, and you have a torus fiber, which is just a circle. And the torus fiber, the length of it gets inverted. So here the base is S1 and the fiber is S1. And generally you have a base is n-dimensional and the fiber is an n-dimensional torus. So why does this make sense as a mirror? Well, now the area is R2 over R1 if we multiply the two sides, and the complex structure is R1 times R2. So the symplectic area and the complex structure have been swapped between the two. So this thing about inverting the length of the fiber is Strominger, Yao, and Zaslow have a paper, mirror symmetry is T-duality. So they say, well, if you have a torus fibration, you get the mirror by taking the same base and the fibers are inverted. This is talking about Calabi-Yau. So a torus, this first Chern class is 0. Mirrors are also studied when the first Chern class is positive. That's called a Fano manifold. And some examples of general type when the first Chern class is negative. The mirrors are not compact in this case. So a lot more can happen if you're not compact, but there's this additional piece of information, which is a holomorphic function from the complex manifold to C. So that's called a Landau-Ginzburg model. So these are mirror to C1 greater than 0 and C1 less than 0. If C1 is equal to 0, the mirror is another Calabi-Yau. Okay, so what about an algebraic version of mirror symmetry? So Kontsevich, in an ICM address, conjectured homological mirror symmetry. So there's an algebraic invariant called the Fukaya category, which I'll define in a moment. That's something on the symplectic manifold. And that is equivalent to, so as categories, something which encodes a complex geometry. This is called the bounded derived category of coherent sheaves. So these two things are isomorphic. That's the algebraic version of mirror symmetry. So we started out, we have a geometric pair of mirrors, complex structure on one, matches a symplectic structure on the other. Now we're taking an algebraic formulation of that. We have a complex category, and we're saying that's isomorphic to a symplectic category. That's homological mirror symmetry. So just for terminology, the symplectic side is usually called the A model, and the complex side is the B model. So what is the A model? So in a category, you need objects, you need morphisms, and you need composition. And as long as the morphisms and composition satisfy associativity and you have an identity, that's a category. So the objects in the Fukaya category are half-dimensional submanifolds on which the symplectic form is 0. That's called a Lagrangian. You can think of Cn, the complex numbers, and then a Lagrangian is Rn, the real numbers inside of that. Given two Lagrangians, so given two objects in our category, we have to say what is an arrow between them? What is a morphism between the two objects? So a morphism is an intersection point of the two objects. So we have, it's actually a chain complex, and it's generated by these intersection points of the two Lagrangians. So Hom from Li to Lj is the sum of the intersection points of the two Lagrangians. There's a differential, so a differential inputs a morphism, and then it outputs something in here. So that means there's two intersection points. There's input one and output one. What can you do with two intersection points? Well, you can count bigons between them. So the number of bigons, that's going to be the coefficient. So composition counts triangles. You can compose 3 morphisms, and you count quadrilaterals. You actually get infinitely many operations this way. All right, so on the B model, DB-Co in these examples, think of line bundles and maps between line bundles. Maps between line bundles, if you've seen Hom with vector bundles, you have Hom from E, say E1 to E2, that's the same as E1 dual tensor E2. So we can concretely write down for DB-Co, Homs are sections of line bundles. This is actually something we can like write down and do calculations with. So Fukai category, that's the symplectic category. We have submanifolds as objects, intersection points or morphisms. On the complex side, on the B model, line bundles and maps between them. So the cases, this conjecture has been proven in a lot of examples, and the ones most relevant for this talk are, so abelian varieties, that's complex tori, you have some affine space and you quotient by a lattice. Polishuk and Zaslow did this in dimension 2, and Fukaya does the general case for abelian varieties. For toric varieties, there's work of Mohammed Abu Zaid, Hanlon, and Hicks and Hanlon. So a toric variety is you have C star to the n, and then you allow some of the coordinates to go to 0 or infinity. So you do a partial compactification. Oops. Hypersurfaces of the toric variety C star n. This was studied by Abu Zaid Aru Kotsarkov, and most recently by Abu Zaid Aru. And hypersurfaces of abelian varieties, this is what me and my collaborators work on. All right, so yeah.
So when you say B model Clark varieties, what you're doing is that you're calling what the B model is here, and then the mirror is well, I guess for like this is like the LG model.
That's right.
Okay, so it's not a good
Yeah, so we're not talking about the Fukaya category on all of these. So B model, that means I'm saying what the complex side is, and then there's some prescription of finding a mirror. And then in these results, they show a isomorphism between for the B model ones, DB-Co of that with the Fukaya category of a Landau-Ginzburg model mirror.
And there's all of the last 3 are on the
Yeah, those are, so hypersurfaces of abelian varieties, that's in the C1 less than 0 general type case. Yeah. All right, so here's a bunch more examples. Genus 2 curve on the A model, B model log Calabi-Yau surfaces, hypersurface cusp singularities, elliptic Hopf surfaces. So there's a bunch of examples that people have done. Co-isotropic, so a generalization of Lagrangian is co-isotropic by Chin. So let's do an example just for the elliptic curve, and more generally for the 2n torus. So this is HMS for the 2 torus. So the idea is, on the left, we have a 2 torus. Objects are, oh my gosh, how much time do I have? Okay. Okay, so slope J lines, that's a half-dimensional submanifold of a 2-dimensional manifold on which the symplectic form vanishes. Slope J lines corresponds to degree J lines on this 2 torus here. You can think of it, so you have on the 2 torus one circle going around this way and one going around this way. You can think of degree J as you have a complex line, and then it has it winds around J times as you go around the torus. So the first Chern class has an interpretation also as a winding number. So slope J lines correspond to degree J line bundles. And composition, so remember that's counting triangles. You can draw these lines on the universal cover and actually count triangles and weight them by area. And that exactly corresponds to multiplying by sections of the mirror line bundles. So you have this Fourier series expansion of theta functions, you multiply them out, you get the same answer. So this is Polishuk and Zaslow. Okay, so more generally for a n-dimensional complex abelian variety, which is a 2 n-dimensional manifold, there's this tau that is the key feature. This is the complex parameter. This is the complex structure that's telling us which complex structure we have on the abelian variety. So that's this lattice that we quotient by is determined by this tau. We're specifically looking at principally polarized abelian varieties. That just means, so you know, like polarization with glass, it's like angled in a certain way. So this is, lattice is angled in a way that allows the abelian variety to emit degree 1 line bundles, so that we have something to be mirrored to. So a generator of the category is, well, if you look at a line bundle on C star n is trivial. So a line bundle on the abelian variety is C star n cross C that respects the lattice. So we have a line bundle of degree 1. And we also have these degree 0 line bundles where we shift, we have a translation map on the abelian variety. And when we do that to one of the line bundles and then multiply by L inverse to get degree 0, we have degree 0 line bundles, a torus worth of them. So what's happening on the A model on the symplectic side, we see, so on the complex side, there's this B and omega that's parameterizing the complex structure. On the symplectic side, we also have a B and an omega that's parameterizing the symplectic structure. So this is the same, the slope J Lagrangians. It's just an analog of that. So J times R is a variable, J is the slope. And we have this B that allows us to translate the Lagrangians. All of the ones in that picture went through 0, but we can translate them to get a family of them. So we have to do that in order to be mirrored to this B. If this B is 0, we don't have to do that. So we have Lagrangians, and they come equipped with a flat connection on the trivial line bundle on them. And the curvature of that one is this B here. So this slope is related to omega, and the curvature of the connection is related to B. All right, so there's a fully faithful functor from dB-co to the Fukai category, which takes the degree J line bundle multiplied by this shift, and that's mirrored to the slope J Lagrangian translated by this Z. So that's the correspondence for abelian varieties. All right, so what about hypersurfaces of abelian varieties? In the case n equals 2, so complex dimension 2 abelian variety is an abelian surface or a 4 torus. Theta divisor, that's the 0 set of a section of this degree 1 line bundle. When n is 2, it turns out to be a genus 2 curve. So here this picture may look familiar from Professor Chan's talk. So this is when we have a genus 2 curve and we want to look at the space of all of the complex structures on it, we have these various degenerations of the genus 2 curve. So this is representing the moduli of complex structures on the genus 2 curve. And that's a theta divisor in the 4 torus, or the abelian surface. So in complex dimension 2, we can actually prove a global homological mirror symmetry result. So not just for a particular complex structure, matching it up with a particular symplectic structure, but actually for all genus 2 curves. So given any complex structure, what is the corresponding symplectic structure? So this is result that I had just for one particular genus 2 curve. And this B that I mentioned earlier was 0. So the B is not 0 in this case, and that introduces a lot of new stuff. So we need to say which symplectic structure corresponds to which complex structure. And this can be understood using the theory in Chan, Mello, and Viviani. So just a definition, when I say Kähler form, that's a type of a symplectic form. And the one that we use is from, thank you, a paper of Cannizzo Lau. So here's how the structures match up. The symplectic structures are glued together in Kähler cones. So this is of the mirror to the genus 2 curve. And they're in one-to-one correspondence with the three-dimensional cones in the Voronoi decomposition. So I haven't defined a lot of things here, but the point is H2 trop is talking about complex structures of the genus 2 curve, and a Voronoi decomposition is how they're glued together. That matches with the symplectic side. Okay, so this is a picture of the decomposition. And how do we get from mirror symmetry for abelian varieties to one for genus 2 curve? You get smaller on the complex side, so you restrict line bundles to the genus 2 curve. And you get larger on the symplectic side. So this 4 torus is now a fiber. So you have a complex plane worth of the 4 torus. So you have Lagrangians in the fiber, which you parallel transport around the base. So that's the picture on the left. There's one singular fiber whose critical locus in dimension 2 is this banana manifold, so 3 bananas glued at the north and south pole. So that kind of looks like a genus 2 curve. It's kind of believable that that would be near to a genus 2 curve. Okay, so the Fukaya category of this one, this is a symplectic fibration on the left here, whose fibers are 4 tori. This Fukaya category of that is the Fukaya Seidel category. So this is just a cool picture. Well, I mean, it's more than a cool picture, but there's a lot of info in it. And that's our theorem. Thank you.